Okay, welcome everyone. Today we're very happy to have Chris Akers from MIT who will tell us about towards better holographic tensor networks.
Thanks. Yeah, and this is work in progress with Red Academy. When we talk to other places these days, I'm talking about some joint work with Jeff that I figured I wouldn't come here and tell him about his work. So, the idea of this is that I have lots of questions about ADS-CFT, and it's difficult to get satisfying answers to these questions without complete control over both sides of the duality and the holographic map that relates them. And one way forward towards answering these questions is to build tractable models of ADS-CFT that we can understand completely and that hopefully capture at least some of the physics we're interested in. And one class of models that have been fairly successful at this go by the name of holographic tensor networks, and in particular random tensor networks that were written down in paper by Patrick Hayden and other people from Stanford in 2016. And so the usual story of random tensor networks is the following. So let me first define for you a tensor. So you basically just start with some 4-part Hilbert space and pick some fiducial state in each Hilbert space that we'll call 0. And these do not need to be the same dimension. They can have different dimensions. And then you basically just pick a random state in that Hilbert space by picking just a tensor, or sorry, a unitary at random from the Haar measure and acting it on that state. So that'll look like this. And often we call this T, which is just the state coefficients, the tensor. And what's nice about this is we can draw it this way. So just for the sake of this talk, I'm going to choose to draw it this way, where there's 3 of these guys are going to be lines that are called in-plane legs. And 1, which I'll draw as a dot, you should imagine is coming out of the board, will later on be something I call a bulk leg. This is an example of a tensor. And with these tensors, you can build more complicated states by, say, taking 2 of them and then connecting them together. And the way that, say, in this paper they talk about connecting the tensors is you pick 1 leg from each, and say the 1 leg from this guy and the 1 prime leg from this guy, and you project them onto the maximum entangled state. Just like sum over I of I. It can be normalized if you want. But the way we draw this would be like this. So this is important. So we've just taken each tensor and then we've drawn a solid line connecting the 1 and the 1 prime leg, and that indicates there's a connection between these tensors. So this just defines some bigger state. And you can construct even more complicated states that are called tensor networks by connecting a lot of these guys together. And I've drawn this circle here to emphasize the geometries that we're interested in, which are basically filled with some tensor network arranged in some hyperbolic way, so that there's more and more tensors as you go outwards. And then there's going to be some number of in-plane legs that cross this circle, and they won't be contracted with any other tensor, they'll just be dangling, so to speak. And I'll call those boundary legs. And again, as I said before, these guys are bulk legs. That's the lingo. And let me now tell you why that is a good lingo. So this tensor network defines one big state on all of the legs, on all the dangling legs. So it defines one big state on the bulk legs and boundary legs. So, in other words, defines the following state, which I might write this way. So this is some T tilde. I'm putting tilde to differentiate it from, say, a T associated with just 1 tensor. And these alpha and beta are just sort of super indices. one big state on the Hilbert space of all the legs that I haven't projected onto the max entangled state. And I could write it this way if I wanted to, where this represents the Hilbert space of all the bulk legs, and this represents the Hilbert space of all the boundary legs. And why we care about this as holographers is that we can regard this T tilde, or really this state, as like a holographic map. So this state, which I'll call T tilde, you can essentially imagine as some map from states in the bulk Hilbert space to states in the boundary Hilbert space. And that map, if you want, you can think of it as you change this to a ket, and then now it literally can act on states in the Hilbert space of the bulk legs and map it to some state in the Hilbert space of the boundary legs. Or a different way, its equivalent is given some psi bulk, you can act psi star, or the star is the complex conjugate, on the states, and then you'll get some other state that's the boundary doing that. So why do you care about this as a map? Well, it's exciting because they have a number of properties that seem to resemble the ADS-CFT dictionary. So the ADS-CFT also has some map where you specify some ADS state and there's some dual CFT state, and it has certain properties. This has very similar properties. So in particular, consider some what I'll call psi tilde on the boundary legs that's prepared in this way, where you pick some bulk state, so some state in the Hilbert space of the bulk legs, and you acted this map on it, and so you've obtained what we'll call psi tilde, some state in the boundary legs. And let's say you want to compute the von Neumann entropy of some subset of the boundary legs that we'll call B in this state, which I'll remind you is defined as you take psi tilde, you trace out B bar, the set of legs that aren't in B. That gives you some reduced density matrix that we'll call rho B, and then the von Neumann entropy is traced to rho B log rho B. So you want to compute this, and it turns out that it's given by a very nice formula. It equals, I'll write it this way, log of d gamma plus Berkeley Center shock plus s of little b psi. So what are these terms? So here we had our tensor network with our boundary legs, and it had some bulk legs all connected to a tensor that was connected to other tensors and so on. And we picked some set of boundary legs that we call B. So let B be this region. And in random tensor networks, we specify some bulk state psi. We had some boundary state psi tilde. And this answer on the right side is, you're supposed to find some surface that we're calling gamma that goes through the tensor network. And by going through the tensor network, we mean all the tensors here have legs connecting them. This surface is defined by the legs that it's cutting. So there's some set of legs being cut by the surface that defines what we mean by the surface in the setting. And all of them have some dimension, right? So a bond is two Hilbert spaces that are maximally entangled. So the dimension of this bond is just the dimension of one of the Hilbert spaces in this entangled state. The total dimension of all the links cut is what's showing up here. So this log d gamma is the dimension of the cut links in this network by the surface gamma, and has an interpretation as the area term in this formula. And then this S of B is, you look at this bulk state psi that you have, you look at the homology region of gamma and B, which in this case is this region little b between gamma and the boundary region B. You consider the reduced state on little b, take psi and trace out the complement, and you compute its entropy, and that's S of little b in the state psi. So what this is supposed to remind you of, why this is exciting, is it's like the quantum extremal surface formula in ADS-CFT. And indeed here, I didn't say how you find the surface gamma. You're supposed to consider all gamma and then pick, the answer is given by the one that minimizes this quantity. So that's very much like the quantum extremal surface formula. You find the minimal surface that actualizes this quantity. So, and of course, this is like the QES formula if you ignore the fact that here there's no time direction. So there's no sense in which it's extreme in the time direction. But that won't bother us right now. This is significant because the quantum extremal surface formula is a very important part of the ADS-CFT dictionary. Right? It basically tells us everything we know about how to reconstruct operators in the CFT from the bulk, which operators are reconstructed and where. QES formula is what people, some in this room, use to compute the page curve, famously, of an evaporating black hole. So that was the exciting connection, is that random Tensor networks seem to have this the same sort of cool feature. Their holographic map resembles the ADS-CFT holographic map. So as a result, random Tensor networks have offered good intuition for how the ADS-CFT dictionary works, because they're easier to wrap your head around, in my opinion, than whatever's going on in ADS-CFT. The only question is, how much can you trust what they're telling you as far as how ADS-CFT works? It's a good question, but at the very least, they have inspired a significant fraction of my work, so that's why I like them so much. But of course, there are obvious shortcomings. So one of them is that even though it very nicely has a formula for the entropy that looks like the formula for entropy in ADS-CFT, it doesn't get other things right, like the range. So the range entropy is this generalization of the von Neumann entropy. Just like this. So remember the von Neumann entropy we wrote in a very similar way, but without the n subscripts. The range entropy limits the von Neumann entropy as n goes to 1. Away from n equals 1, it's given by this. I believe this is right. Assuming rho is normalized. And if you try and compute this quantity in random Tensor networks, what you get is something like, what you get is basically something that very much looks like the other formula we got. So what's important is that this term is exactly the same. That it didn't depend on n. And in the context we care about, this is the leading order piece. So you can take some large bond dimension limit, and this is much bigger than this. So in fact, I will mostly not even really be caring about this piece. So in this sense, in that limit, the Rayleigh entropies are all the same. They're independent of it. This is bad because gravity has a very different answer. So gravity, or if you were trying, if B was some subregion of a holographic CFT, you could use the bulk dual to compute it. You wouldn't get this. You would get something that's more like, it depends on little a. It's like, sorry, I hope that you can read this. It's like 1 plus 1 over n over 2 times S1 at leading order, something like this. So it very much depends on little n. It's not a constant. And if you want to ask, well, why are the random tensor network, why are they getting this wrong? And you trace back to the reason why it's constant here. It's the links. So we decided to project, connect the tensors by projecting onto some maximally entangled state. And it's the fact that they're maximally entangled. Right, so if you compute the Rayleigh entropy of one side of the maximally entangled state, all the Rayleigh entropies are flat, right? They're all constant. So they're the same thing. So you might try to fix this by saying, okay, let's not connect all tensors by the maximally entangled state. Let's connect them by some other state, like two tensors. Maybe I'll connect them with some state that's not maximally entangled. It might be thermally entangled. And indeed, that would make the Rayleigh entropies not flat, or not constant, but not in the right way. So it wouldn't fix the issues. For example, if you compute the Rayleigh entropy for some B that's not just some connected subregion of the boundary, but instead it's like some disconnected region. It's computed by essentially the positions or the areas of some branes that have tension, and that tension means that they backreact with geometry and therefore affect each other. And that effect is not at all accounted for by just projecting all the links on some particular non-flat states. So the real source of the issue is not that it's the maximally entangled state that we're projecting onto, it's that it's just some fixed state that we're projecting onto. It needs to be something that isn't fixed. Or something, That would be your guess. So the question is...
When you say that it's not fixed, how do you mean that it varies from link to link? Or
from state to state it varies. That's actually what I'm going to get to next, is how we're going to fix this problem. So you could ask, you could just say, well, we're not really getting the Rayleigh entropies right. What do we make of this? Your first thought might be, okay, random tensor networks were cute, but they're just limited models, and they can't get the details of everything in ADS-CFT. In particular, they can't get the details of the Rayleigh entropies right. Maybe we should just move on from it. That could be your first thought. And your second thought, though, could be, but maybe we'll learn something by trying to reconcile this issue with ADS-CFT, by trying to make tensor networks look like ADS-CFT a little more. Maybe we'll learn something. And indeed...
Sorry, this is a relevant comment to some extent. You keep saying that, you're saying ADS-CFT, but you really just mean look with small same. I mean, this is just...
Yeah, right, so this
this
one
is
limited...
ADS-CFT.
Right, I want to make tensor networks match just Lucas-Montesana limited aspect of ADS-CFT at this point.
It's the gravitational pattern. You'd have all the same problems in any other background. And all the same solutions for them.
That's right. It's really the gravitational path integral I want to match, although maybe it does a better job of modeling ADS-CFT in the sense than some other situation, in the sense that I have some boundary Hilbert space that is different from the bulk Hilbert space. I'm computing like entropy of subregions of that. If this were supposed to be consider or something, boundary Hilbert space, I guess tensor networks would be trivial. I wouldn't even know how to start asking about the entropy of subregions.
Sure, but you can always cut out some region.
Yeah, you can do that. You mean like in the style of U and Jeff?
Well, even, I mean, just at the level of these tensor networks, right?
Yeah.
But if taking some tensor network, tiled flat, so asymptotic flat space-time where they,
That's right, yeah.
Cut it off somewhere. It would look more or less the same, and I think we'd have all the same issues.
You would, yeah. Yeah, I guess in this flat space example, I'm not sure what to expect about the entropy of regions at the spatial boundary of this region you cut up.
Well,
Okay, so noticing this mismatch of range entropies, I'm going to leave that picture of the tensor up there. In 2018, some groups, or two groups, one being me and Pratik, and one is people Don and Merrill, proposed a way to reconcile what tensor networks are doing with what happens in gravity. And the idea was to start considering what are called fixed area states. In gravity. So these are states where, let's say, this is a time slice of ADS. Consider, say, let's say this is an extremal surface from this boundary point to this boundary point. It has some area A. There's some operator that measures this area A. And in this quantum theory of gravity, the background is not some fixed static thing. It has fluctuations. And in regular states, the fluctuations, so the QES formula, remember, was something like, if this is your boundary subregion B, and you want to compute the entropy of B, leading order, it's given by, we usually say, like A over 4G. This maybe should be understood to be the expectation value of this area operator that measures the area of the extremal surface. And usually they have, the area has fluctuation, in a semi-classical limit of small g Newton, the area is some tightly peaked Gaussian, so the fluctuations are not zero. They're like order 1 over square root g Newton. The fluctuations in this quantity, like the fluctuations in A are order square root g Newton, so the fluctuations in A over 4g are like 1 over square root g Newton. And it is these fluctuations that are responsible for the fact that if you were to compute the Rayleigh entropy of B, it's not going to be constant. The Rayleigh entropies are sort of more sensitive to the sort of subleading parts of the state. So the idea is that you can consider fixed area states where you're kind of projecting onto an eigenstate, or really an approximate eigenstate of this area operator. So we're going to fix it to be something, say, order 1. So it's a much smaller fluctuation window than order 1 over square root g Newton, and the limit that g Newton is very small. the units are, well, anyways, and it was argued in these papers by, from 2018, by critiquing me and Don Carlo Maroff, that to the extent that you could define these states of gravity, their boundary duals have roughly flat entanglement spectra. And so the idea was that maybe these tensor networks are modeling these states. So maybe this breathes some life into using tensor networks to understand ADS-CFT. It's like, okay, maybe they don't model these general states that you had in mind with fluctuating geometries, but they sort of model these ones where you sort of fix the area at the extreme surfaces. And a general state, here we've sort of projected onto some eigenstate or approximate eigenstate of some operator. A general state would be some superposition of such states. And so you might imagine you can model a general state in ADS-CFT as some superposition of tensor networks, perhaps with different geometries. That was the idea for the hope. So let me write it down just to spell out what the hope was. The idea was that tensor networks are like fixed area states. And a general state in gravity was something like a superposition of fixed area states. And then therefore, some superposition appropriately interpreted of tensor networks was like a good model for a general state in gravity. So that was why, at least I cared about these results so much, is that this was giving us a foothold for a good twin model. Okay, so that was like 2018, but then soon afterwards, all of my hopes were dashed by someone in this room who I will call out. So Jeff soon after, with a paper with Ning and John Soros and Aaron Wall, it's a very interesting paper where they do a few things. So I think 90% of the paper is arguing that there's sort of a cool way of building a tensor network that models ADS-CFT or gravity. And then the other 10% of the paper is proving a no-go theorem that says no tensor network could ever model ADS-CFT or gravity. And I think it's
10% is more interesting than 90%.
Yeah, I completely agree. So that 10% is much more interesting than 90%. In fact, it's still haunted me to this day. It is the reason why I'm talking to you right now, because I'm going to try and fix the horrible problem that they left us. So what they point out, first of all, is that when we have these tensor networks, say this is a tensor network, I'm not going to draw all the legs on all the tensors. It's not just one area that we're fixing. So it's not like we picked one extremal surface and we're fixing this area. We're fixing all of them simultaneously. So this area is fixed, so is this one, so is this one, so is this one, and so on and so on. The areas of all cuts you can make the tensor network are simultaneously fixed. So all of these regions defined by these cuts, like let's say this one was the extremal surface of B, and this one was the extremal surface of some region C. They all have flat radius spectrum simultaneously. And so I'm going to write that down because it's very important. In tensor networks, all areas fixed simultaneously. And the idea was that in gravity, what they pointed out is that this isn't possible. So while you might be able to fix the area of one surface, you can't simultaneously fix the area of all surfaces. In fact, you can't fix the area of, say, this surface and the surface that crosses it. And here's why.
Isn't that the statement that you can construct a tensor network tool to fix the area of gravity states?
It's a statement that,
Got that backwards.
right, tensor networks,
You can't construct a gravity tool to tensor network.
Yes.
They were not. That was
Yes.
the statement, right?
Right.
Not that you can't construct a tensor network tool to gravity.
yes, whatever tensor networks are modeling is not any gravitational state.
Yeah. But you
There's
could try
some
to fix it on the
qualifications
other-
about the tensor network, like, like random tensor network.
Yeah.
Tensor networks where you have sort of isometries from the RT surface to the boundary, basically, from all RT surfaces to the boundary.
Yeah.
So it's non-asymmetric.
That won't be the point here, but the point here will be, let me first just give you the flavor of the argument that they gave. So, so the argument I want to make is just that, let's say this is a time slice of ADS. And I had two regions, A, which was this region, and B, which is this region. And so they have QES, gamma A and gamma B. And I want to say fix the area of gamma B and fix the area of gamma A. That's what I would like to do. But let's see what happens first when I fix the area of gamma B. So the problem is that the operator that measures the area of gamma A is conjugate in gravity to the boost angle across the surface. So if you were to fix the area of gamma B so it doesn't have large fluctuations, say you fix it over 1, then there's large fluctuations in the boost across the surface. And gamma A is an extremal surface. And so its position, it now becomes it becomes uncertain. Its area becomes highly uncertain by the uncertainty in the boost angle across the surface. That's the flavor of the idea. Yeah. One thing you might be confused by is that you could try and specify some initial data on this slice where you're specifying the metric intrinsic to the slice, and that feels like it's specifying the areas of all surfaces. But the point is that these are both extremal surfaces, so if you're just specifying the metric intrinsic to the slice, you're not at all specifying the intrinsic curvature of the slice in space-time. And so the positions, it's just not going to be, there's not going to be some nice solution where both extremal surfaces lie on that one slice.
If you fix the area of gamma B a lot, like I don't know, there's some amount, wouldn't it roughly destroy the future and pass gamma B, and so the extremal surface in that space-time would have to cross gamma B?
Yeah, so let's see. So people study this like Lorentzian.
I just mean somehow
It's a very high curvature region, or
Think about for example, if you measure the bifurcation surface really precisely, you just create like a fluctuation, superposition of time shifted thermals. And then there's surfaces going through the wormhole still, and any of those things.
no, but which one would dominate? The question is, right?
There would just be large fluctuations, and I think the expectation of a surface going through from one end, the extremal surface going through from one end to the other will be very large, because probably the wormhole is very long.
Yeah, the expectation is large. So yeah, at least, especially in this case that Jeff is describing, it's not the case that the future is destroyed. I mean, I think what you're pointing out is there's this work by Pratik and Don where they find the Lorentzian space-times of these fixed areas. They have shocks on the future of the fixed area surfaces. I'm not sure that
those mainly come from if you try to fix the area to be something that classically different from what it would be naively. I think if you fix it to its classical expectation value, then think all that's going to happen is you have this sort of superposition of places.
Is it clear that, is there a difference between classical and quantum effects in the ball? Like fixing the area of, I see, you're saying you want to fix it at the value, at the expectation value in the quantum state.
Yes, so say you have the term put up, you can imagine fixing it to like some totally different area to the normal horizon area, and that would be like projecting.
Then somehow this would fix this problem, though. But it might not be the interesting thing to consider.
It wouldn't fix this problem because you still have the even if you're fixing it to be like its classical expectation value, you're destroying the fluctuations in it. So therefore, you're necessarily creating fluctuations and boost angular velocity. It's uncertainty principle. So that means it's sort of like it's like a very floppy geometry on that time slice, and then the future and past. I don't know. The seven field double case is very simple. For AES winner, it would be simple. In general, it might be weirder. But anyway, I think we should let Chris keep going.
Yeah. Thanks. Okay. Yeah. So it's in this sense So if you say fix gamma b to have say order 1 fluctuations, a over 4g to be order 1 fluctuations, then gamma a will be fluctuations in general like order 1 over g. Very large. So my slogan, my way of saying this will be that the area operators don't compute. Because you can't fix the fluctuations of one without blowing up the fluctuations of the other. So the areas don't compute. So again, we're faced with a situation where tensor networks seem like they're not modeling something that gravity does. And your first thought might be, again, okay, tensor networks are limited models and can't get this feature, time to give up on them. But then your second thought, which is the perspective that I want to take, is that maybe we'll learn something by trying to reconcile tensor networks with this feature. Maybe we'll fail and we'll learn something. Or maybe we'll succeed, we'll learn even more, and we'll end up with an even better model to help our intuition about how ADS-CFT and gravity work. So, I want to tell you what I figured out so far about the story. I don't have a complete answer yet, but we have gained some appreciation for what will and won't be part of the reconciliation. And to explain to you the reconciliation, we first need to re-understand what tensor networks are. So, I explained the sort of canonical way of constructing tensor networks that I think most people are familiar with. But it's not my favorite way of doing it, and I talked to Michael Walter, and it's not his favorite way either, so by authority, it shouldn't be your favorite either. I'm going to give you a different way of building up the same network. And it's not a new way or a new understanding. The random tensor network paper also had this way of thinking about them, but it's somehow not the one they caught on. So, but it's the more fruitful way for generalizing these models. So remember, we ended up with some network like this that defined a map from the bulk legs to the boundary legs, which we basically got by, we had a bunch of tensors, which were like states like this. Here I'm writing like sum over t, some of the indices of this t, some of the indices of this t prime, etc. And then we projected all of them onto some maximally entangled states between all the links, etc. And then this constructed the tensor network. But instead of doing that, I want to do something that's equivalent, but I want to start by laying down all of the bulk legs and all of the in-plane legs. So my picture would start without tensors, just the legs. So it might look like this. So these dots are like what I was calling the bulk legs over there, and these lines are what were the in-plane legs over there. So this is defining, so here, this is some Hilbert space, and some state in this Hilbert space would look like this. Okay, so some state on the bulk legs with the dots, and then so far we were just considering states that with the maximum entangled state on all the links. So this drawing corresponds to this state. And then now what I want to do is let tensor, which I might draw similar to before, be defined as a draw. So before it was a ket, now it's a draw. And we're going to consider a collection of tensors as one big map. So a collection of tensors will now look like this. And they're not connected together. We have not projected any of their links onto some maximum entangled state. So they're just some collection of tensors, and they would act on some Hilbert space that looks like this. So maybe this collection of tensors acts on a Hilbert space like this. Okay, so by this parentheses, I'm trying to say, you have this object, which I'm going to regard as the map. It's acting on some state in this Hilbert space. It's mapping you to some state on, just say like the boundary legs. So this is sort of mathematically equivalent. I'm just sort of replacing which ones I'm calling the draws and which ones I'm calling the kets. So the tensor network, I'm just thinking of as these disconnected tensors, and they act on states that are in this Hilbert space, and they map me to a boundary state. The benefit of this way of thinking about it is that we can now reinterpret the in-plane legs as part of H bulk. So we can say like this whole thing is H bulk, and then the idea is really the same as before. The tensors are just a map from H bulk to H boundary, but this H bulk, already in orange to emphasize, now includes the link over spaces. And this is important because we can imagine now there might be different bulk states that have different states on the links. So the links could be degrees of freedom like in a lattice gauge theory. So what I'm going to actually do momentarily is imagine we have a bulk theory that might be defined on some lattice like this, where there's degrees of freedom on the edges. In fact, like a lattice gauge theory that lives on the edges, and there could be matter at the vertices and so on. And then the idea will be maybe we can cook up some bulk theory such that the area of crossing quantum minimal surfaces don't leave. Okay, so the first guess would be to have H bulk be some non-abelian lattice gauge theory. I don't know if this was your first guess. This is my first guess. It was my first guess because lattice gauge theory has some degrees of freedom on the links, and so there's going to be some area operator associated to the state. It's different, gives you a different area for different states in the links, as I'll explain momentarily. And because it's a non-abelian lattice gauge theory, maybe the area operators will not commute. So this isn't going to work, but it's not going to work for important reasons. Generalize momentarily. So the idea again is like we have some lattice gauge theory. This is the bulk Hilbert space, and then the tensors are just a map from this lattice gauge Hilbert space to some boundary Hilbert space. And we want to understand let's say we were to pick some boundary region B and compute its entropy, as before, it would be given by the area of some cut through here. And what is the area now? In terms of this lattice gauge theory. And it's going to be convenient for me to just tell you a little bit about Hamiltonian lattice gauge theory. It's not too bad. So the idea is that forget about matter. So we're just going to have some degrees of freedom on the links, nothing at the vertices. That'll be the simplest case. And let's start from the Hilbert space of one link. So this link is going to be like, say that link. This is the Hilbert space of this link is what we'll call HG for G, whatever the group is that we're talking about. Let's let it be some compact group or just some finite group. Actually, that would be the easiest. So you might imagine, right, this is just Hilbert space of some particle living on the manifold of this group, say, and it's spanned by states that I might write this way, where G is some element of capital B. So this is like the position basis for states in this Hilbert space. And there's also a basis, there's a conjugate basis called the Europe basis that is often written this way, mu ij. This is just like a conjugate basis to this one related by some version of the Fourier transform, where this mu labels the irreducible representation of the group, and this I and J indices are indices within that Europe. So the idea is, if you had some group element G, you can consider as many different irreducible representations, which we could label by mu, and the mu. So this is some matrix. This is some irreducible representation of G. The matrix is in vector space. And I and J here are the indices of that matrix. So this guy is related to this guy. This is just the Dirac notation for these wave functions. These details aren't super important. What's going to be important, I'll mention momentarily. I'm just trying to motivate for you what the area will be in this case, and explain to you that in this case it's going to compute, so it's not going to solve the problem. So for one link that was the Hilbert space. The Hilbert space of the entire lattice gauge theory is something like HG tensor n, where n is the number of links we have, modded by the Gauss constraint. So this is literally just the constraint that you're familiar with, the Gauss constraint. In this language, it's the one that basically makes, in this basis, makes it so these all fuse together correctly at each of the vertices. So them fusing together correctly is like charge being conserved at all the vertices. So so the Hilbert space doesn't factorize into all the different links. It does. You're in the subspace where these are all constrained at each of the vertices in the appropriate way. So what's important is that now we need to decide how the tensors will act on these links. And this is kind of tricky. Let's just look at one of the links. In general, it's going to try it. There's going to be two tensors that want to act on it to map it to the boundary state, but it's just one Hilbert space. So how do we decide in the holographic map how do two tensors act on this one Hilbert space? Basically, what you have to do is use the so-called extended Hilbert space construction, which maps this one link into a particular state on two links. And the way it does that is it maps, in this basis, some state uij, which is on this link, to this particular state. The exact form doesn't matter. What's going to matter is that there's going to be a lot of entanglement between these two links that it creates. So it's something over this k index. The reason it has this is a natural extension is that this is the extension that satisfies Gauss's law at the cut. So it's like you're cutting the link here, reimagining it as two links, and demanding that Gauss's law is satisfied in the new vertex you created. And so that's the only state that does that.
Chris, can I ask a question?
Yeah.
So could you remind me, in lattice gauge theory, this group element G is given by the Wilson loop between the two links, is that right? It's e to the I integral of A between.
Yeah, it's like e to the, yeah, it's like,
You're just breaking into the Wilson loop on the left over there.
this integrated along some line is like the G that we're associating with that link.
And you're just breaking into the Wilson loop there.
Yes, we're just dividing the Wilson line in a natural way. So the idea, I don't want to get too bogged down in these details. The idea is that there's a natural way to let this non-abelian lattice gauge theory be the bulk Hilbert space, and have the tensors act on them to map it to some boundary state. But what you get, unfortunately, is not non-commuting areas. What you get is that so here's the lattice gauge theory in here. If I had this be on boundary region B, and I was computing its entropy, it would be given by, in following these rules, you just learn that it's given by some area operator that is like the area of this guy, L1, plus the area of this guy, L2, L3, and so on. So, in other words, the entropy of B is, in this case, is given by the expectation value of psi, the bulk state, inside of some area operator that's like L1 plus L2, etc. Where L1 is like the area associated to this link, and then L2 is some entropy area associated to this link, and so on. And that's bad because if A was this region that's crossing, and its area was given by the expectation value of this operator, this area touches these links, and these are entirely different links. So the purple area and the blue area have to commute because they're acting on two entirely different links, two sets of different links.
Chris, in general, in lattice gauge theory, you can have sort of excitations that don't live at the boundary. Right? Presumably you wanted this to be a special sort of lattice gauge theory where that doesn't happen, so that the final Hilbert space really is just a tensor product with things to the boundary.
Yeah, there's not really gauge theory is not like holographic in the sense of graphic.
Yeah.
So it's not getting all of this.
So you're just not trying to get that, you're just trying to...
That's right. That's right. Yeah, so this is sort of like some first attempts that definitely doesn't capture that and doesn't even capture non-commuting areas. So in the little time I have left, I want to tell you about what you can do. So this is still in the preliminary stages, so take it with a grain of salt. But what I think helps you get a tensor network that resolves the non-commuting areas problem. And that is, so yeah, this first guess didn't work. Can we make a guess that does work? Maybe what we want to do is be a little smarter with how we're making our guesses and not just come up with some bulk Hilbert space that we hope has the property we want. we can try, ideally we would just take gravity, make that our Hilbert space, and see how it resolves this non-Euclidean problem. But it's difficult to put gravity on the lattice, which is the only version of Tensor network I understand. So we can't quite do that. But actually we can do something that's one step in that direction, which is we can take 2 plus 1 dimensional gravity, reformulate it. People already know how to reformulate this as some sort of topological field theory, and we can put that topological field theory on the lattice, let that be our Hilbert space, and see how that resolves the non-Euclidean problem. Okay, so this is what we're doing. And when you do this, gravity actually has a number of features. The field theory that's equivalent to gravity has a number of features that are different from non-Euclidean lattice gauge theory. There's like 5 new ingredients. I'm just going to focus on one new ingredient that is, I think, the one that resolves the problem, that does the trick here. That new ingredient is that it's the new ingredient that really makes it topological. Anyways, it's like this if you also add what we'll call the flatness constraint. So I'll tell you what the flatness constraint is, but by add the flatness constraint, I mean the Hilbert space is no longer HG tensor n mod Gauss. It's HG tensor n mod Gauss times the flatness constraint. So there's extra constraints. And what it is if you have your, say, your lattice, consider it in the G basis, the position basis, for a moment. So to each link, there's some state assigned, some like G assigned to every link, say G1, G2, G3, G4. And then the flatness constraint is the constraint that this ordered product of them is the idea. So this has to be true for every little plaquette. And this makes it topological for reasons I don't have time to really go into, but the idea is that, like, let's say you're computing some Wilson loop like this. You're evaluating its expectation value in some state. Well, by the constraints, you could ask, what's the expectation value of this Wilson loop times some like little plaquette here, something like that. And this is actually just some little deformation of this Wilson loop into this loop. And so you can add in these little deformations for free. That doesn't change the expectation value of the Wilson loops. And so
this is just the gravity of the Chern-Simons theory, not a Yang-Ross theory, right?
Yes. Yeah. Exactly. Yeah. And right now I was just trying to explain the Chern-Simons theory, or the topological field theory. And the idea is that with this extra constraint, it's now a topological theory. Different Wilson lines are the same operator if they're related, if they're topologically equivalent. So the reason this matters, the reason this can change the story at all, is that
the topological property already assures that you're going to push the state out to the boundary, right? Is that?
You could do that.
So we're back to that. Yeah.
Yeah. So now this has property.
Is it enough to enforce this constraint like locally? I guess because you're enforcing it as flat. I was going to say like Wilson loops in a non-Euclidean theory are not just a product of little Wilson loops. But I think if the curvature is 0 locally, then that tells you that all Wilson loops are 0. So yeah.
Right. Yeah, it's important.
So how hard would it be to generalize that to non-flat geometries? Is it really important that it's?
I think it means flat in this sense, that it equals the identity and not some like other fixed G.
Yeah.
Because then it would be much more complicated, but yeah. Or an identity system maybe.
But if you somehow specify a fixed G for every whatever smallest loop, would would that have the same effect of pushing the state?
I think it would actually. If you specify it for all the G's.
So G is not, the curvature is not gauge invariant. So you could take a trace of it or something in some representation. This is actually why it's not a product. It's just because you need to take a trace or something to. So having it be equal to the identity is a gauge invariant statement because the identity is unique in its conjugacy class, but otherwise you can only specify the conjugacy class, and then I think it's complicated.
But it's just a technical limitation. I mean, it makes it easier to write down something concrete.
Yeah.
It is, right? But it doesn't mean that.
Probably. I'm not saying you can't do anything. That's
Yeah.
just not really.
Chris, what condition in gravity does this come from?
Yeah, so this is, let's see, how would you like me to answer that? Like the map from, I don't know if I have a satisfying answer for you. It's like it's kind of an ugly transformation to get from gravity to the topological field theory.
It's basically the Einstein
Right.
Right,
you wonder
the
why?
Einstein equation. It's the equation of motion.
Right.
The equation of motion is just, the first order or whatever, so it's constrained rather than it's just the 3D Einstein equation.
I thought in non-Helian insurance time is like dA plus A wedge A equals 0.
You're saying like, sorry, is your question this thing? If you, insurance Simons, it's like A wedge GA plus A wedge A, you know, like where this is flatness, it when you vary A with respect to A because it gives you equals 0. Right. And then what's harder to see is how it also gives you Gauss, but insurance Simons it's like this is equivalent to Gauss when you just recognize what components of A are equivalent to what other components of A.
Yeah, I thought F equals 0 implied that this was equal to E as well when you had abelian insurance Simons. You're saying that's also true for non-abelian insurance Simons? I'm just not familiar.
Yeah. That's right. That's right. Yeah, this is like
F is always the limit of the small
Right, okay.
Yeah, I don't want to hold on here too long. So what I want to say is that the reason why this changes the story, it can give you non-feeding areas, is there's a few different perspectives you can take, but maybe the clearest is to say, recall before, with just the Gauss constraint, the area was something like the sum of all the areas along the length. And these areas were essentially electric operators. They were operators that were diagonal on the mu basis, this like mu ij basis. So they just sort of measure what that each link was in. And none of these, not even their sum, is physical anymore. They don't commute with the flatness constraint. So you can't use them. They can't be in the center of the algebra, because they're not even in the algebra. So the area operator should be something in the center of the algebra, because 1 should be in the algebra, and 2 should be in the center because it's measurable from both sides. Well, the operator you had before doesn't satisfy in the algebra part, so it's no good. And so now you have to say, okay, well, great, what is in the center? And the answer is what are called ribbon operators. And they're sort of a combination of electric and magnetic guys. So again, I'm drawing a lattice. And so if I wanted to have this be my region, little b, I want to consider what's in the center of this algebra. It's going to be an operator that morally has some, it's a ribbon operator, that's what they're called. It has some magnetic part here and also acts on these links. And what it does.
I'm a little confused about that.
Yeah, so here, sorry, I was trying to draw. This is supposed to be a little b. I'm considering a situation like this where now I'm I'm imagining that I want to ask about what's in the center of this bulk algebra. Because the area operator will be something that's in the center of this bulk algebra.
And do you mean a little b in your example to the left? You mean everything to the right, you know, the vertical pink line?
Yes, I mean everything. I'm trying to talk about this right region, and I need to engage theory. I have to sort of decide what I mean by a subregion. One way of doing that is picking some algebra that's usually has a center, and the center is related to some properties of the surface, the bounding surface between the two regions. So here I'm considering an algebra where to define little b, that's all of the operators on this side, and the center is some ribbon operator. And the ribbon operator, I can tell you exactly what it is, but essentially it's a Wilson line here, and also, so it's like a magnetic part here, so something that's diagonal on a G basis, together with some electric operator here, so something that's diagonal on a mu basis. And there's particular combinations of these that are physical. You can use both constraints. And so this will be in the center of the algebra. And
no local central operators, is that true?
that's my understanding. I'm almost sure that's true. I haven't
Are there still bulk lengths here somewhere?
Yeah, you could add an adder that has both lengths. For now, I'm not doing that. And what's important about these ribbon operators is, let's consider this situation where I want to just consider the, so let little a be like the entanglement wedge of capital A, and little b is the entanglement wedge of capital B. So little a, so b was like this right half, little a will be like the bottom half. And what's in the center of little a, so the candidates for the area operator, are guys that look like the ribbon operators that have magnetic pieces here, coming with electric pieces here. And what's important is the ribbon operators that cross don't commute. And you can sort of see this. This is very plausible because right here, they're acting on the same links with conjugate operators. So the purple guy acted the magnetic operator here, while the red guy acted with an electric operator here, and vice versa there. And this is basic, this is basic.
So if you want to measure the same area from the complement of B, of little b, is there some, I mean, the way you drew the operator looks sort of asymmetric, but is there some relation that
Yes,
forces
yes, Gauss. The Gauss's law allows you to push the electric guys into side. Exactly. So that's the upshot. So this would naturally imply some sort of non-commuting areas. I want again to emphasize that you should take this story with a grain of salt because it's true about the ribbon operators being in the center and so on. The story isn't complete because I haven't figured out how that's supposed to map to a particular extended Hilbert space prescription that works with the tensor network. But the progress is that this lattice gauge theory seems to have some natural notion of non-commuting areas. But it's another deal to try and reconcile that with the tensors. But anyways, let me conclude by saying, if this is to be believed, then it seems like we'll get some tensor network-like model with non-commuting areas by incorporating some extra constraints that gravity has, like flatness. And one thing this teaches us is that the area operator is not like this purely electric operator. I think this has often been the picture that people have, where they imagine that there's this extended Hilbert space story in non-abelian lattice gauge theory, and people want to understand the Ryu-Takanagi area as like the log dim-R term there, if you're familiar with that. This would say it's more complicated than that. It's not like the log dim-R of this electric center. It's more like whatever the eigenvalues are of the ribbon operators. So it's more complicated than just that log to mark term. And they suggest a different picture for how factorization works in gravity than I had before appreciated. It's not that, when you factorize across some cut, that there's just some local degrees of freedom on the surface, like we had before, where the area was just L1 here plus L12 here plus L3 here, and so on, where you could localize the area contributions. Here, the area operators are very much intrinsically these non-local guys. The edge modes are more non-local. So factorization in this model requires a story about ribbon operators, which have the algebra of Hop algebras of quantum groups, and all of this I want to explore more.